Welcome to Concerned Citizens Presents. Concerned Citizens of Laguna Woods is an organization dedicated to peace, economic and social justice, good government, and a clean environment. Every month, we invite an expert to enlighten us on a topic related to our mission. Because Village TV videotapes these presentations, we can share that expertise with a larger audience. We hope you enjoy today's broadcast.
All right. Well, thanks for having me. And I know it's been a while in coming. I know, so I'm glad this ended up working out. And how I hesitate to say fortuitous, but how strikingly relevant it is to be speaking today, one of the hottest March days ever observed in the western U.S. I'm speaking to you today from Boulder, Colorado, at about 5,600 feet in elevation, so a little over a mile up in elevation, and it is currently 85 degrees Fahrenheit here. So the 95 degree plus weather in the San Fernando Valley this week is extraordinary, but in some ways the Mountain West is seeing an even more, in relative terms, extraordinary event in the sense that these are just not temperatures that we should be seeing at a time of year which is typically the last big month of snowpack accumulation. But it is not only shorts and t-shirts weather, but it's getting a little bit beyond comfortable be outside in shorts and t-shirts weather already, which is really just, as a climate scientist, really quite amazing to behold. But so with that present context in mind, and I did, by the way, slip one slide in here just 15 minutes ago before we started with today's numbers on them, because I do think it's interesting to look at the bigger picture in the context of the local immediate picture too. I do want to talk a little bit more broadly about the California context of a warming climate. So that's the main subject of today's conversation. Hopefully, all of you in an air-conditioned room while we go through this. All right, so the big picture, literally in this case, if you zoom out to the scale of planet Earth, which is the scale that I often like to emphasize before we get into the details locally, uh, I update this map every year. It comes from NASA, I guess, and it's not like the big picture changes every year. Of course, there's a lot of orange and a lot of red on the map, meaning that the whole world essentially is warming. But I do like to update this every year because over the years it becomes even more orange and even more red than before. But also because there are some interesting spatial patterns that emerge in the global data. So not everywhere on Earth is warming at the same rate. And there's a couple of key pieces we can glean from this. So far, the Earth on average, on a sort of a decadal average basis, is warmed by about 1.3 or 1.4 degrees Celsius, or about 2.5 degrees Fahrenheit, as of 2022. But the last couple of years have been a bit of a stair step above that. So we've seen more like 1.5 or nearly 3 degrees Fahrenheit of global warming the last couple of years, as we've seen a little bit of a step up in the warming rate above what we'd seen previously. But the main thing I really like to emphasize with the global map is again that spatial pattern of warming is not uniform. So there are some places warming faster than others. And there's two general patterns that really jump out. One is that, as is pretty obvious, the Arctic, the high latitudes up at the top of the map, far north, are warming much faster than everywhere else. In fact, they're warming on the order of 3 or even 4 times as fast in the Arctic as the rest of the world on average. And in fact, I checked this morning, Arctic sea ice is as of today at a record low level this morning for all of the observed period. So it's really putting an exclamation point on that accelerated warming trend up there in the high latitudes. But the other pattern that is maybe a little more relevant directly to California is that virtually all global land areas are themselves warming faster than the oceans, which then means, for the math to pencil out, that the continents are warming much faster than the global average. So when we talk about the Earth having warmed 1.3, 1.5 degrees Celsius so far, what that actually means is that most of the continents, and therefore most of all the places where people actually live, since there are relatively few of us who live permanently out on the open ocean, I suspect, has warmed by about 2 or 2.5 degrees Celsius already. So if we live on land, we're already living in a 2+ degree warmer future because the land is warming that much faster than the ocean. So what's causing the warming? Well, we've probably all heard at this point of the greenhouse effect, with this mechanism by which the Earth likes to hold on to some of the incoming solar energy that might otherwise escape back out to space by virtue of heat trapping gases that exist in our atmosphere. If we didn't have any greenhouse effect, we'd live on a miserably cold planet that was mostly covered in ice. So the greenhouse effect itself is not necessarily a bad thing. It's what makes the Earth what it is today. It makes it habitable across a wide range of latitudes. But the problem is we're greatly enhancing that background erstwhile greenhouse effect. And this is where global warming comes from, through that accumulation of additional heat trapping greenhouse gases in the atmosphere well beyond what would have been up there but for human activities that include but aren't limited to fossil fuel burning, land use change, I think clearing land for agriculture and urban development, things like that, all of which result in the net emission of these heat trapping gases. And as of now, this 2025, 2026 era, we now have the highest carbon dioxide levels in the atmosphere, carbon dioxide being the leading greenhouse gas globally in the atmosphere, the highest level we've had in over 800,000 years. So certainly no one alive today, or even anyone alive in any modern generation of humans that's ever experienced carbon dioxide level that's anywhere near close to what we've got floating out there in the air that we are breathing right now. So where are we headed? There has been a lot of progress with green energy, and I think you've probably heard about this in the news, and it's quite real. So that's the good news, is that we are generating more electricity, for example, from minimally or non-carbon polluting sources than ever before. But the problem is the atmosphere doesn't really care about our best intentions. It cares about how much carbon is actually entering the atmosphere, not whether the fraction of green energy is increasing, but whether the total amount of dirty energy essentially is decreasing. And so far, we've not really bent that carbon curve, the one that fundamentally matters for warming. And so we can see that the rate of warming is continuing, perhaps even increasing a bit. 2025, December 2025, we reached a new record high for peak carbon emissions for per year. So you can kind of see from all these plots on here, and there's a lot of squiggles and details you don't need to see, but essentially, even if you're in the back of the room and maybe this is a little bit small, the point is all of these plots are increasing to the right. So the temperature plot in white is increasing as we go forward in time. Carbon dioxide is rapidly increasing as we go forward in time, as is methane, nitrous oxide. All of these are the key greenhouse gases. What this means is that we're currently on a path to about double the amount of warming we've seen so far, with an expectation that doubling that warming would result in a lot more than doubling of the impacts we've seen, because we start to hit thresholds and trigger points that essentially mean that doubling the warming has a much larger relative effect each time you double it. So the reason I mention this is just to emphasize that even though it's critically important to solve the underlying problem of global warming by bringing our greenhouse gas emissions down as fast as we can and eventually close to zero, that's what we need to do to solve the underlying problem. We also, in the meantime, really do need to be thinking about what we can do to make extreme weather and potential disasters less hazardous as they become more prevalent or more extreme. So essentially, we need to also engage in climate adaptation to make the best of what we've got, take stock of the reality that we are going to see a significant amount of more warming, and no matter what progress we make, there will be more warming before we get there, and more, greater increases in extreme events like heat waves and heavy downpours and wildfires. So, what do we do to increase our resilience to those kinds of events in the meantime while we simultaneously work to solve that underlying problem of the warming itself? This is something that probably requires no explanation, and I realize the title here actually says Orange County because we're essentially we're well, all of you are currently in Orange County, and so this is quite locally relevant here. And this plot, by the way, is updated all the way through January of this year, so this is right up to the moment valid. Uh, it's obvious that it's warmer than it used to be. I probably don't need to tell any of you this, but especially on a day like today. But this is not just a fluke. If this current ridiculous March heat wave were truly a fluke, I'd feel a lot better about it because it would mean that, well, we got unlucky, but we probably won't get unlucky again. But unfortunately, what this really tells us, the long-term warming, is that it's not a fluke and that we should expect it to happen again, and that eventually we'll see even greater heat waves at even more unusual times of year. So this warming trend on an annual average, if we go back to the first half of the 20th century, so you go back prior to 1950, average annual temperature in Orange County was right around 62 degrees Fahrenheit, and today it's closer to 65, even 66, depending on the year, which might not sound like a lot. And the difference between 62 and 66, if that's actually what you're experiencing, is maybe light sweater versus slightly less light sweater. But the real challenge is everything else that the several degrees of warming has actually brought about. It isn't the incremental change in temperature that's the biggest problem, but it's what this means for the shift in extreme heat events, for extreme precipitation and wildfires, things like that. This story is not that different for California. Obviously the numbers are a bit different for different parts of the state, but the picture is the same, and all of California's warmest years on record now have occurred in the last 15 years, as well as none of California's coolest years on record. So, just looking back over the past decade and a half of your life, you've probably experienced all of the warmest years you've ever experienced and none of the coldest years. And of course, that would not be true were it not for the case of the rapidly warming climate. And this is even more true for heat waves. We actually see that the most extreme heat in California has increased at about 2 to 3 times the rate of ordinary temperatures. So we actually have a lot more warming on the most extreme days. And this is a plot specifically for summer heat wave temperatures, maximum temperatures. So it doesn't necessarily apply directly to March, but it just means that in general, the most extreme heat so far has actually increased at a more rapid pace than more ordinary conditions. And we actually see that all of California's top four warmest summers have now occurred in the last 10 years amid very rapid summer warming, particularly since the 1970s. So here, we saw some warming prior to the 1980s, but not that much in terms of extreme summer temperatures. But where we've really taken off is from the 1980s onward. And this is sometimes something that I like to reflect on when folks in Southern California say, "Yeah, well, isn't this just the urban heat island effect? Didn't we expand our suburbs and our paved areas a lot in the 20th century?" And that's true, we did, and we did amplify the urban heat island effect in a lot of Southern California over that period. But a lot of that development occurred up through and prior to the mid 1980s. A lot of the suburbs that are around in Southern California today, not all of them, but most of them, they were already built circa 1985. But the vast majority of the warming we've seen now, especially in the most extreme temperatures, has occurred since that period of rapid suburban growth largely leveled off. So it clearly isn't the main factor here. We clearly have a much bigger change at play. And this gets me to what I really want to emphasize beyond temperatures, which is that it isn't just the temperatures that matters. In fact, a lot of the time we talk about warming temperatures in a warming climate, but that's mainly, it's almost a secondary concern to the kinds of reasons why it matters most. So I want to introduce the notion or the analogy, the expression, if you will, of the expanding atmospheric sponge. This is something that probably everybody in the room has used in their own kitchen at some point in your lifetime. Just an ordinary kitchen sponge capable of absorbing liquid, water spilled on a kitchen counter or something. Imagine that your ordinary kitchen sponge magically expands to become about 4% larger for every degree Fahrenheit of warming, or about 7% larger for every degree Celsius of warming. That is essentially how the air actually behaves in a warming atmosphere. So we actually see an increasing capacity for the air itself to hold water in vapor form simply by virtue of a rising temperature. And this is an exponential process. This is not something that is gradual or incremental, but in fact, the degree to which that expanding atmospheric sponge expands for each degree of warming is larger than the last. Think about it like compound interest. 4% compound interest if you got it in a savings account, that's pretty good. It won't beat the market, but it's still a decent rate of return. But imagine you actually experience many compoundings of that 4%, and all of a sudden you got a much larger number. That's the magic behind compounding in terms of savings and investment, also why your credit card interest is so dangerous. The same thing is happening with the atmosphere in terms of its capacity to hold water vapor. And the reason why this matters is that if the atmosphere is saturated, well, the expanded atmospheric sponge can hold even more water. And if you wring out, if you will, the figurative atmospheric sponge when it is saturated, it's going to yield more water. So that's analogous to heavier downpours. And in Southern California, we actually saw one of the wettest starts to the water year on record this year, believe it or not. October through December of 2025 was in LA County, Ventura, and Santa Barbara counties, the wettest such period on record in over 100 years of record keeping. So depending on where you live, if you're on which side of the county line you're on, you may have seen your wettest start to any water year on record, even as in those same places we also saw our warmest start to the water year on record, and now continuing into March, the ridiculously warmest start to any calendar year on record as well. But the other reason why this matters is not just because it increases the likelihood of very extreme precipitation events on the one hand, the subtle secondary but very important feature that this also produces is an increase in the atmospheric thirstiness, the air's demand for water, its propensity to extract water back out of the landscape, evaporate water from soil, from bodies of water, and even from plants. So it's a double-edged sword, or it's two sides of the same coin, to mix some metaphors and some expressions, but essentially by virtue of this the relatively well understood thermodynamic process, this expanding atmospheric sponge effect, which dates back to physical chemistry experiments that were originally run in the mid 1800s. So this isn't some uh, simple prediction from some complicated numerical model, but this was lab science from the 1860s, essentially, that turns out to be very relevant in a modern context. The net effect of this is that we should expect to see increasing what we call hydroclimate whiplash, increasingly wide swings between wet and dry, as that expanded atmospheric sponge, when it is saturated, yields heavier rainfall, and when it is dry, yields faster rates of evaporation, worse droughts, worse wildfires, and yet doesn't tell us a lot about what happens in between, because a warming atmosphere does not tell us whether that larger atmospheric sponge is in fact actually saturated or not at any given moment. So what we see globally, there's a lot of data on this, but just essentially, especially if you're at the back of the room, just think of it this way. This is a global map where some places are shaded in purple and some places are shaded in brown. And if you're struggling to find the brown region, well, that's because there aren't very many of them. The point is, anywhere where there's a purple shading is a place where we expect to see significant increases in hydroclimate whiplash, the swinginess between extreme wet and extreme dry. And just to really drive the point home, it's virtually everywhere. There's more extreme increases in some regions than others, but the only places we expect to see decreases are over remote subtropical ocean regions, which again, not really a place where too many humans alive actually live. So for all intents and purposes, almost every human living on a continent somewhere in the world will experience an increase in hydroclimate whiplash with 2 to 3 degrees of warming, which again, I will reemphasize, is exactly the median estimate for where we are still headed. So why do we care? Well, here's a Southern California specific example from a few years ago that now feels positively ancient history given everything that's happened since 2017. But just to remind folks, the Thomas Fire in Ventura County in December of 2017 was at the time the largest wildfire in modern state history. That's since been eclipsed several times since then. It was immediately followed by a very localized but very intense downpour of rain in early January in Santa Barbara County. The fire did cross the county line, which resulted in a devastating mud flow and debris flow. It killed quite a few people and destroyed a lot of homes. But if we look at the climatological average, if you purely just mathematically do the average of the conditions over these 2 months, we might characterize this period as a period that was mostly sunny, breezy, decidedly breezy, with below average precipitation overall. So my point being is that if we consider only changes in average climate, like over this period, for example, we're going to completely miss the point for all of the events that we actually should be worried about, not these minor deviations from the norm and it's slightly cooler or warmer or wetter or drier than average, but when it is way outside the norm, when we see these huge swings between extremes on opposite ends of the spectrum. So what is going on in California? Well, interestingly, there's not much of a trend in annual average precipitation. There's been a little bit of a decrease in recent years, but it's not really statistically detectable. It's quite small. California's average annual precipitation has stayed relatively steady, although it remains highly variable. And yet, over the very same period, using the very same data set, we've seen a huge increase in both the frequency and also the severity of drought. In fact, by this metric, we've been experiencing a drought whenever it isn't flooding, essentially, in California. So, how does that pencil out? Well, one reason is that we've seen an increase in the variability of moisture, increasing swinginess, if you will. Uh, Harkens back to the expanding atmospheric sponge. But I'll get more into this in a moment. A Northern California example, just to sort of drive the point home, here's a sequence of events over about a decade. Again, it's hard for me to believe this is only over about 10 years, but we have the worst drought, at least since the 1970s, and by some metrics, the worst drought we've ever observed. Then catastrophic wildfires. Remember the Tubbs fire in Santa Rosa. Then pretty severe flooding just a couple of years later in exactly the same places in Sonoma County, and then more extreme fire that destroyed a lot of structures. Again in 2020, that was a terrible fire year in California. Back to another episode of historically severe drought, very much comparable once again to the 2014 drought, which is then comparable to the 1970s drought, if not a bit worse, in 2021. And then widespread inundation once again in 2024. And if I had space for yet another panel, I probably could have added yet another swing back in the opposite direction. California does have, to be fair, a really high natural intrinsic hydroclimate variability. So, if you live in Orange County, you're well aware that we have a drought every year in coastal California that's known somewhat jokingly in some communities as summer. It's always dry in the summer. It's literally headline news if it rains in LA in July or August, which occasionally it does, but when it does, it is literally the only story on the news that night. That's how rare it is. Turns out that's globally unusual. Most places in the world actually see most of their rainfall during the warm season, so in summer, or they have a more uniform distribution of precipitation throughout the calendar year, wet and cool, or sorry, warm and cool seasons together. So California already has a built-in seasonal drought every year, known as summer, and a built-in pluvial period, known as winter. It turns out that this is part of the reason why California has the ecology that it does, because we tend to get our moisture delivered to us during the time of year when we don't need it as much, and we have to rely off what we get from a given winter during the long, dry, warm season when it isn't raining in most places. And this not only defines the climatology and the ecology of the region, but it also means that it makes the region susceptible to both drought and flood because we really only have one season every year when we're going to get whatever we're going to get water-wise. That's winter. And if we miss out on that winter, we really are we're out of luck until at best the following winter. So we're guaranteed to not to be potentially under the gun until the relief we get the following winter. And then if we have another bad year, all it takes is two bad years in a row to be in a pretty serious multi-year drought. Because again, we're not going to get, we know in advance, we're not really going to get meaningful replenishment in the spring, summer, or fall. We really do have to wait for the next wet winter. Likewise, because California, for the most part, it does have deserts, but most of California is not, in fact, actually a desert. We do actually have a lot of water that falls in some parts of the state. The North Coast, there are rainforests, and there's vast swaths of coniferous forests all throughout the Coast Ranges, the Sierra Nevada, and yes, even in the higher mountains of Southern California, even within LA County, San Bernardino Mountains, San Diego County Mountains, etc. And so we actually do need a significant amount of water every year, and that comes in winter. So in order for that math to pencil out, we know it isn't going to fall really in the summer, and really probably not in the fall or spring most of the time to a significant degree. So that means it must come in winter. That leaves the state susceptible to flood because it means we know on average we do actually receive a significant amount of precipitation, but it all comes in a 3 or 4 month window. And so sometimes when it rains, it pours and it can be a little too much too quickly. And that's kind of the signature here. So what do we expect moving forward? Well, and here's what's interesting. And these large systems of equations that we call climate models, these are essentially vast million line computer programs that are run on some of the largest supercomputers in the world to project weather and future climate also. They suggest that there may be relatively modest changes in California's annual average precipitation, maybe a slight decrease in Southern California, a slight increase in the north, but not huge changes on average, which some have taken to mean that there won't be much meaningful change in California's hydroclimate. But I think that really could not be farther from the truth. You just got to look beyond the average. Those very same climate models suggest that there will be a robust increase in the very wettest years and the wettest individual storms. Again, all we have to do is go back to earlier in this wet season. October through December 2025 in Southern California was the single wettest start to any water year we've ever observed. So this fits into that. And remember, before the severe LA fires of January 2025, we had two exceptionally wet years in Southern California immediately prior, and I'll talk a little bit more about that in a moment. So we actually do have recent examples of extremely wet years and extremely wet individual storms, but those very same models suggest that the likelihood of extremely dry years also increases, which leads to this increase in what we call precipitation whiplash. So we really got to look beyond the mean because once we look beyond the mean, almost everything is expected to change. And the modest or insignificant changes in the mean are really just a statistical distraction from all of the stuff that really does appear to be changing, both in the real world and in model projections. So this is true even seasonally, by the way, where we expect our already short and sharp seasonality, wet winter, dry summer, to become even more pronounced. So we won't suddenly flip to wet summer, dry winter. Fortunately, that does not appear to be in the cards. You'll still recognize the seasonal cycle, but it may become even shorter and even sharper, where the shoulder seasons, the autumn and the spring, may become drier. This spring is certainly shaping up to be a dry one in Southern California, following a very wet winter, so this would certainly fit the bill. That means we have a longer dry season, but also a more intense wet season, and that has big implications for ecosystems, for wildfire, for agriculture, and water supply, all of which are very much in the news right now, despite a year where the precipitation was really not that much below average. We also expect to see in a warming climate, think about the wet side of the expanding atmospheric sponge, stronger and moister atmospheric river storms. Now, atmospheric rivers are a keystone feature of California climate. They're not new. They've always been around. They will always be around. And if we didn't have them, we wouldn't have much water in California. So LA would not exist, nor would most of the rest of coastal Southern California cities and towns were it not for atmospheric rivers. So can't live without them, but sometimes it's hard to live with them too when they bring too much all at once in the form of flooding. And in fact, 95 to 99% of all historical flood losses in California are associated with atmospheric rivers, although so too is about 60 to 70% of all of our water supply. So again, blessing or curse depending on the context. But the real challenge we expect to see with atmospheric rivers in a warming climate is that as the expanding atmospheric sponge, well, expands, it opens up the door to atmospheric rivers, these plumes of highly concentrated atmospheric water vapor moving quickly in the air above your head, pushed by strong winds, to atmospheric rivers that are of unprecedented magnitude and contain more moisture than ever before experienced with their historical counterparts. So that opens the door to more severe floods, especially during winter, than we've become accustomed to historically. And there's considerable concern that we're a little bit underprepared for the risk of a severe flood in California. And believe it or not, there are large swaths even of Los Angeles and Orange counties that are within large historical floodplains. We managed the flood risk over much of the 20 and so far in the 21st century pretty well, but there is a question whether we will continue to be able to do so with the infrastructure built for a climate that frankly no longer exists, but especially will be out of sync with the climate we're going to have in just a couple of decades from now. So we think that there's already been about a doubling of the likelihood of a really serious statewide flood event as we've sort of been quietly, well, not so quietly worried about about drought and wildfire because we've experienced a lot of those in recent years, unfortunately. But quietly in the background, this risk of a severe statewide flood, we believe, has about doubled already. And we see glimpses of that, hints of that in record-breaking individual downpours in certain parts of the state, or record wet starts for the rainy season, just like we saw in LA this year. But we haven't yet seen the big one in terms of flooding. Fortunately, I'm glad that we haven't. But this is something that's percolating there on the back burner, and at some point, it won't be so much on the back burner anymore. Um, and so when it comes to drought, sort of already covered this, but just think of the dry side of the expanding atmospheric sponge. How is it that the same amount of rain and snow as we used to get is leading to more droughts? Well, the answer is that it just doesn't go as far as it used to. But this is not a statement about human consumption of water. That's a whole different story. I'm purely talking about the water cycle itself, evaporation and precipitation. And the reason is that that same amount of water falling from the sky is falling on fewer days with greater concentration. The fact that it's less distributed means that more of it becomes runoff and less of it soaks in. We're seeing more intensive evaporation during the dry periods in between rain events. I mean, just think about how much evaporation is occurring during this record-breaking March heat wave following what was a very wet start to the winter. There's a lot of water evaporating still out of the soil from plants, bodies of water, etc. We have less snowpack, certainly this year is a good example of this, and shorter snow accumulation seasons. And so, one way to think about this is that droughts used to have hot or cold droughts. We could have a precipitation deficit and it might be warmer than average or it might be colder than average. But by virtue of the historical warming that we've seen, essentially all droughts today are hot droughts by historical standards. We don't really get cold droughts anymore, and so temperatures are always an aggravating as opposed to an alleviating factor in all of them. So, one challenge here is that we actually expect that the very heaviest rainfall, whether it's from an atmospheric river or a thunderstorm downpour or something else, that's what's going to increase the most. But we actually expect to see decreases in the more light to moderate precipitation. So, fewer gentle rain events and more torrential downpours, with greater soil drawing in between those events and thirstier air pretty much all the time. And the net result of this is potentially that we don't necessarily see more frequent ordinary floods, but that we see more severe extraordinary floods. And what I mean by this is that the kinds of floods that we would expect to see somewhat more regularly. So think about the moderate severity floods we might get every 5 to 20 years, something that the average person would see several of at least in their lifetime. Those floods might not be increasing, and indeed, globally, they don't necessarily appear to be, which some have taken to mean that climate change won't increase flood risk. But what actually appears to be happening is that by virtue of these competing effects, the expanding atmospheric sponge resulting in more intensive evaporation and soil drawing most of the time, but more extreme precipitation precisely in the most extreme moments, what this leads to is a divergence, a threshold below which floods stay the same or even decrease because the soil is drier and it absorbs more of that light to moderate or even locally heavy rain. But once you reach past that critical threshold of soil saturation, the very most extreme precipitation events are going to completely overwhelm the soil's ability to absorb more water anyway. And as those events are the ones that preferentially are going to intensify the most, this means that the most extreme floods might increase by a large margin, even as the most gentle floods, the ones that might serve as erstwhile reminders that we need to prepare for flooding, probably won't increase at all. And that represents a major challenge for climate adaptation, because how do you articulate to folks that you're not seeing an increase in the frequency of mild to moderate floods, so why should we be preparing for an increase in the very most severe ones? Well, the thermodynamics gives us a little bit of an answer as to why that could be the case, and indeed probably is. So that brings me to wildfire. And I know a lot of folks are thinking about that in the middle of a record-breaking March heat wave. We do know that historical trends have resulted in a very large increase in the number of extreme fire and weather days, so more than a doubling during autumn already since the 1980s. And again, that's really not that long of a period of time in the scheme of things. So, over a 40-year period, a doubling of anything is a lot when it comes to extreme event risk. The main factor behind this is just that we have vegetation that is on average drier over what is on average a longer and hotter fire season. That increases not only the number of days per year on which we can see fires in the first place, but maybe more importantly, it increases the intensity, the rate of spread, and the potential destructiveness of those fires that do occur. And it also increases the likelihood that we see dry vegetation conditions overlapping with very windy conditions, which, as you know, in coastal Southern California, are, those Santa Ana winds are most common from late fall into winter. So the longer we stretch that fire season into late fall and into winter, the bigger the problem becomes. Even if the winds themselves are not changing, even if all that's changing is the dryness of vegetation, it just means that the overlap between the two is expanding. So, another consequence of this directly with respect to wildfire, I think, is illustrated pretty tragically by what happened in LA last year, where we actually exited a near record wet period from 2023 to 2024 at UCLA campuses was the second wettest 2 year period on record as of April 2024. So, a superlative on the wet side. That led to a period of exceptional vegetation accumulation in grass and shrubland, or in particular in chaparral type ecosystems, which are predominant in coastal Southern California. Uh, that was immediately followed by a period of record heat inland, at least, and atmospheric thirstiness during summer and autumn of 2024, but maybe more importantly, by a complete failure of the rainy season to arrive in autumn 2024, continuing all the way through January 2025. Record low precipitation, record high atmospheric evaporative demand, a really big atmospheric sponge that was, in this case, dry. Think about it. This led to a period of remarkable vegetation desiccation. So, going back to the wet period, we had about a doubling of the usual amount of what's known as herbaceous biomass. So, think of a well-watered lawn grows more lushly. That's kind of what happened here. And then we had the driest period on record immediately thereafter that kind of kiln dried all of that dead, dry grass and everything else. And that was immediately followed by one of the strongest offshore wind events on record, again, with the failure of the rainy season in January 2025. We all know what happened next, but I just added another arrow to this plot last month because in autumn 2025, we've gone all the way back to record wet. But depending on what happens over the next few weeks, I may be able to add yet another arrow back in the other direction, pointing to record heat and a rapid redevelopment of drought conditions in the Southwest. So, you know, we're living this reality. I mean, this as recently as earlier in my career, and as you've probably recognized, I'm relatively young. This was a prediction about the future, and increasingly, this is just an observed reality about the present, where every passing year that goes by that I give these kinds of presentations, I have a new empirical and sometimes rather tragic data point to share regarding just how this is unfolding in our own daily lives. That does give you an opportunity to have a slightly less dramatic infographic here that I think is useful in understanding what I mean by the wildfire connection to hydroclimate whiplash. Think of the progression temporally from really wet conditions with lots of vegetation growth to then really dry conditions where things become really flammable. This is primarily relevant, this fuel accumulation through growth of grass and seasonal shrubs, and then desiccation where it dries out to critically or even record dry levels. This is typically linked to increased grass and shrub fire intensity. So it's not necessarily going to apply everywhere across all ecosystems, but specifically in grassland and shrubland type ecosystems where there's a lot of variation from year to year in how much growth of actual grass and brush there is, this is often the dynamic we see at play. And in fact, it's also the dynamic that we see is increasing rapidly in a warming climate. We've, again, seen it all around us in spades in recent years. But I did want to emphasize that this is a little bit different than the dynamic in forests. So when we talk about forest fires specifically, or wildfires occurring in primarily forested settings, to put some scientific language on it, that those generally are going to occur following periods of dryness. So there, your gut instinct is kind of what applies when it comes to wildfire. Drier equals more flammable in forests. And if you think about it, the reason for this is that the trees can't get up and walk away year to year. Dry year, wet year, the trees are largely there to stay. Over decades, maybe things can change, but year to year, wet year, dry year, the same trees are in the same place regardless, and they're just going to be a lot more flammable during a severe drought than following a wet period. But it is different in grassland and shrubland settings where you actually do have a lot of variation last year to this year to next year in how much fuel is actually available. But here's the problem. In a warming climate, we see more of both. We see both increased frequency and magnitude of these transitions from extremely wet to extremely dry. Those would be the periods you'd see more fire activity in shrubland and grassland ecosystems, like we saw with the January 2025 fires in Southern California. And in the periods that are extremely dry, we would expect to see more forest fire activity. So during periods of severe or worsening drought, that's when the forest fires will follow. And that may be more what we see this year, where we see really low snowpack, for example, in the Sierra Nevada and the northern mountains up by Shasta and really throughout the American West. this may be a more active forest fire season at higher elevations, precisely following this kind of progression. We do see, contrary to some claims in the popular press, that there has in fact been a large increase in the severity of fire weather conditions, specifically in winter in coastal Southern California. We ginned up this data analysis in quick response last year to the LA fires because we were very frustrated to hear in the newspaper headlines and on television, even sometimes, in conversations with scientists, we're like, well, we don't know if there's really been such a significant increase in, Southern California is special. It's different than forest fire risk, which is true for the reasons I just mentioned. But despite that, we still, in fact, see a large increase in the severity of fire weather conditions during Santa Ana wind season. And this is not primarily occurring because the Santa Ana winds themselves are changing. We don't really think that they're going to increase in a warming climate. In fact, there's some evidence they might slightly, nominally decrease, but that doesn't really appear to be driving the trend. What really seems to be driving this trend is a dramatic increase in warmth, vegetation dryness, and the overlap between dry vegetation and windy conditions. In Southern California, it really is those dry, windy periods that drive almost all of the major fire risk. And just to emphasize something, because I know there's a lot of folks who have experienced pretty terrible things in recent years in California when it comes to fire, and I've unfortunately had yet another occasion to add another photograph to the sequence. It's not that wildfire itself is inherently bad. That is part of a natural process on the landscape. The problem is the intersection between wildfire and populated areas, which has become, well, an increasingly big problem as we've seen expanding wildfire disasters. So I think for me, the question, the burning question, if you will, is not even can we decouple, but will we decouple fire from catastrophe? Because we do know that it's possible. We do know that we can reduce risk to communities through various measures. The question is whether we are going to do it quickly enough to stave off the erstwhile increase in fire risk that's coming from a warming climate and other factors. That I think remains an open question. But I think the question, hopefully, we can frame this constructively around will we do it? Not is it possible? Because it is possible, but it's a question of whether we're actually going to achieve those outcomes. Uh, and there is also sea level rise. And of course, where you are on the coast affects how susceptible you are to sea level rise. Sometimes even being, 5 or 10 feet up on a coastal bluff is enough to insulate a fair bit from this. But there are parts of coastal Southern California, including, of course, the immediate coastal zone, the beaches, and some of the lower lying parts of LA County and Orange County, and then, of course, farther north in Northern California, where sea level rise is a challenge. Sea level rise is actually accelerating, so the sea level is rising at an increasing rate with each passing year. In fact, it's doubled just in the last 30 years, that rate of rise. So again, a very significant change over the course of my professional career. Interestingly, in California, more than half of the sea level rise that we expect moving forward is actually attributable directly to the melting of continental ice sheets. So single most important factor for how rapid sea level rise will be in California moving forward is what happens to Antarctica. And that's kind of wild if you think about it, but the whole ocean is sloshing away from the South Pole as the volume increases. Uh, and so I won't belabor the point too much here, but really what this just tells us, it's just another moving part that we're being squeezed in multiple directions by multiple stressors, and we do have to think about how to manage and optimize our interventions to respond to all of these simultaneously. Okay, so summing it up, what do we expect in a warming California? Well, the climate will remain familiar. It's still going to be warmer in the summer. It's still going to be cooler in the winter. Usually, this week is a pretty extraordinary exception to that. But as I point out, those variations are going to be more and more volatile. Increased swinginess, more extreme heat extremes, more extreme wildfire extremes, and more extreme water extremes on both ends of the spectrum, wet and dry. The only thing that's not up on here on this list is any record-breaking Arctic outbreaks. If you're worried about that, I can put your fears to rest. Warmer still, though, as I mentioned, with rising water and wildfire whiplash really seems to be the name of the game. So to sum it all up, how are we going to adapt? And I think that the bottom line is that we need to be able to roll with the punches, so to speak, flexible and proactive, climate interventions and adaptations are going to be the name of the game. Um, not interventions that improve our resilience to one kind of potential hazard only. So not only drought, but thinking about what kinds of water management and flood management interventions that improve our resilience to flood and to drought simultaneously without inhibiting our ability to respond to the other. So we don't want to engage in something to protect against drought risk if it increases our exposure to flooding, because we know that both are likely to increase, for example. This means, in some cases, things like fighting fire with fire, more prescribed burning. It means learning to live with fire, thinking about how we build and maintain our structures and vegetation in our communities differently so that it's more resilient to the fires that inevitably come. Thinking about floodplain restoration, in other words, letting rivers do their thing within some controlled bounds, letting controlled floods happen within certain bounds, focusing on groundwater sustainability and cleverly reoperating our existing infrastructure in a way that can accommodate our shifting reality. So, in a lot of ways, this is a short way of saying look for co-beneficial opportunities for both society and the environment. And I would be remiss if I didn't put in some real-time data, given that we are all living through in the American West one of the hottest March days ever observed, going back at least into the 1800s, so I presume in all of our lifetimes. Uh, this is a snapshot from 1 p.m. Pacific time today, so I believe a little bit less than 2 hours ago. I actually would expect the map as of 3 p.m. closer to now would look even more stark. Uh, but what this map is showing are locations that are currently experiencing record-breaking temperatures. Yellow dots are places that are nearly tying daily records. Red dots are places that are breaking the current calendar date record. So the warmest temperature on record for, I suppose it's March 19th. But the purple dots, and I know it's a little bit hard to distinguish from the red, but just I assure you that there are many of them in California, Nevada, Utah, Arizona, New Mexico, Colorado, Wyoming, Idaho, Montana, and some other states as well. Those are locations that are right now, as we sit here, currently experiencing the single hottest temperature that's ever been observed on any March day in that location's history. There are so many locations right now. This is hard to count, and it's true from sea level on the Pacific coast. It's true nearly 2 miles up in elevation in the Rocky Mountains. It's true from Canada to the Mexican border. It's true from San Francisco to Kansas City. That is how big this current heat wave is. It really is. I'm sort of at a loss for words in terms of superlatives. So if you hear about this in the news, it really is a newsworthy event. And with that, I think I'll close with some time for discussion. And I just wanted to acknowledge again the California Institute for Water Resources and the University of California Agricultural and Natural Resources, so the extension of the University of California system, which is where I am employed. And through that, it means I'm able to have conversations on a Thursday afternoon with groups like yours. So if you appreciate this, UC always likes to hear back from folks who are on the receiving end of the weather and climate communication activities that we do. And there is a QR code up on the screen. You can take a photo of it. Your phone will recognize it. I realize that that doesn't always work for everybody. So if you're interested in filling out the survey and you can't access that QR code directly by taking a photograph or using your phone camera, just shoot me an email via the email on the left that's also printed on screen, and I can send you the link directly as well. So thank you, and I think we got some time for discussion, if I'm not mistaken.
Thank you so much for a really splendid presentation, very clear, and your slides, well, they're fantastic. I don't know how people make these slides, uh, but in any event, they are spectacular. We have people going around now, right? They're writing cards on questions on note cards. While we're collecting a few, I do have a couple of starter questions. So let me throw this one at you. This is from me. Given our current trajectory, When do you expect climate motivated mass migration to the United States to start? And from where would you predict that climate related migration to the United States would come from?
Well, that's a good big picture question. I think we're already there. There's some there's some social science and climate science joint research that suggests that there's already been significant outmigration from parts of Central America where the warming we've seen so far has made it a lot more difficult for folks who are working in agriculture because working outdoors during some of the most extreme heat of the year has become intolerable, and some of the crops aren't doing so well. There's been outmigration to Europe from the Middle East and Africa in recent years, arguably for similar reasons. So it's not certainly not the only reason we're seeing this, but like with anything else, the migration question is partly one of, is climate change a risk multiplier or a motivation multiplier? If there were already pre-existing concerns or issues where you're living, if you have, a climate tinged extreme event that really pushes you beyond your ability to manage that on a recurring basis, that's really going to potentially increase your individual motivation or your necessity to leave where you are and go somewhere else. So I think this is already sort of baked in, if you will, to some of the political tensions and recent events surrounding sort of backlash to immigration in Western Europe and in the United States and in other countries. And it's something that's kind of lurking there in the background, largely unacknowledged. Again, not independent of other reasons why people might want to emigrate from where they are, but again, I think we're already sort of living in that moment now, and I think the migration patterns are, they're not always going to be in the same direction either. And we see conflict in the Middle East. I mean, I don't think it's entirely coincidental right now that Iran was, and in particular the capital Tehran, was about to run out of potable water due to the worst drought on record there. Is it the only reason why we're seeing this war sort of expand and go poorly in the way that it is right now? Certainly not, but is it part of the reason that set the geopolitical stage for escalating tensions and has shaped the way that the people in the region have responded to it? Now, setting aside governments for a moment, but the actual people in these countries. We've seen climate-related extremes precipitate a number of recent geopolitical conflicts. Again, never the singular cause, I don't think, but there's a lot of but for type questions. Would it have evolved as it did but for, the historically severe drought occurring when and as it did? And I think that
I'm going to interrupt you, okay?
there's a serious question there.
Yeah, that was my filler. We have quite a few other questions here
Great.
that maybe you could answer a little bit more briefly, because we have quite a few, some of which I think are not that complex to answer. So here's one. Since we live in a desert, should we stop planting grass?
Yes. Well, it depends where you live, and there certainly could be some people in an Orange County venue who do live in a true desert. Although much of coastal Southern California is not a true desert, as I mentioned, there are true deserts in Southern California once you go inland. But regardless, I think we're sort of at the point where probably yes, you probably should be thinking about not planting grass because especially this. Um, there's this notion of what's called in the water world non-functional turf. This is the grass you might see on parking lots or roadway medians or decorative in front of office buildings. And how often do you actually see anybody in an office building go out and play on the grass in front of their place of work? Not very often. Those are the most obvious places where we probably shouldn't be growing grass anymore. But I think even in a residential context, there's a lot more grass than is probably justified by the amount of water that's available. And in a wet year, it might not be so much of a problem, but in the dry years, it really does become an issue. And I know that water agencies all throughout the Southwest are strongly incentivizing first getting rid of the really kind of low-hanging fruit of this non-functional turf, but also thinking seriously about landscaping decisions at the individual property and homeowner level of there's a lot of other things you can do that are interesting and even beautiful and functional instead of, well-watered lawns. And that probably is the direction that everybody should be at least be thinking about in Southern California. Whether or not you happen to live in a part of Southern California that's a true desert or is merely semi-arid.
Okay, thank you. I don't know if you know the answer to this. Are there plans to reservoir catch the water during the wet extremes in California?
Yes, the short answer is yes, and we already do this, and we're trying to get better at it. The problem is there's this mismatch of scale in the sense that California's water systems, particularly Northern California, which is where most of the water comes from, even for Southern California, they're predicated on capturing water from winter storms and protecting the watersheds from some flood risk by sort of buffering. So you can kind of control the outflow from the reservoirs and kind of artificially control what the river flow is. But so they're both flood control and water storage mechanisms. But the problem is, even the largest, enormous reservoirs in Northern California are only capable of capturing the amount of water that's contained in approximately one large winter storm system. So what that means is if you fill up on the first storm, your reservoir is full. You can't add additional water storage. And again, these are already some of the largest dams in the country. These are not small structures that can be expanded or build more of them or anything like that. They're already huge. It's just that it is structurally very difficult to capture a large fraction of the water that falls, as it does in California, in huge volumes very quickly all at once. And so we built our system predicated on the convenient fact that in the Sierra Nevada, historically, you'd have an enormous buildup of snow water equivalent. So you'd have a lot of water stored in the snowpack that began to accumulate in October or November and then reached a peak around March or April. Now, as you know, that certainly isn't going to be the case this year. We have a rapidly declining snowpack already as of mid-March, amid record heat. And the reason why that's a problem is right now, we pretty much have to let all that water go. It's melting. You might think, oh, it's all going to be in the reservoirs, so it doesn't matter if it melts early, but it does melt. It does matter because we can only store so much of it. And once you reach a certain critical safety margin where you can no longer let the reservoir level rise any higher, or you're actually at risk of causing a serious situation if a big storm does come later in March or April, in terms of flood risk, a lot of that water is going to flow right through the reservoir, down the river, into the delta, and out to the ocean. And so in this warming world with the snowmelt shift, yes, we're capturing as much of that water as we can. We're trying to be clever about eking up a little bit those safety margins a little bit higher than they used to be. This is known as forecast informed reservoir operations. Essentially, it takes into account the fact that, well, we looked at the weather forecast, and there's a 0% chance of a significant storm this week, so we don't have to plan as if, a huge atmospheric river could come out of nowhere right now. We know it's not going to, so we can afford to top up the reservoir a little bit. Like topping up the tank of gas in your car. By the way, don't do that either because it results in a lot more hydrocarbon emissions directly to the atmosphere. But it's okay to do in a reservoir in this context because it's just water. Anyway, we're trying to do the best we can with this, but there's a limit because these reservoirs can only store so much a fraction of this water. And so the short answer is yes, but a warming climate is affecting our ability to do so successfully.